A car slams its brakes at 60 kilometers per hour. A ball is dropped from a building. A sprinter explodes off the blocks. What do all of these have in common? They are all examples of motion in a straight line, and in this chapter we are going to understand exactly what is happening mathematically and physically. We will start with what position and displacement actually mean and why they are not the same as distance. Then we will build velocity and acceleration from scratch using calculus, not just memorizing formulas. We will derive the three equations of motion step by step, tackle free fall under gravity, and solve stopping distance problems. By the end, motion will not just be something you see, it will be something you can read, predict, and calculate. Let's get into it. Imagine you're driving a car along a winding road. Your GPS shows you're at a certain location, but how do we describe motion mathematically? Position is simply a coordinate on an axis. If we set the starting point as 0 and the road runs east, then positions to the east are positive and positions to the west are negative. But here's the catch. If the car follows a winding path, the total distance it actually travels, called path length, is longer than the straight line distance. Path length is the total distance covered. Displacement is the net change in position, calculated as final position minus initial position. Delta x equals x2 minus x1. Let's say the car drove 3 kilometers along the winding road, but ended up only 2 kilometers east of where it started. The path length is 3 kilometers, but the displacement is 2 kilometers east. If the car had turned around and gone back 1 kilometer west at the end, its final position would be at 1 kilometer east. The displacement would be 1 kilometer, and we'd write displacement equals positive 1 meter. Two runners compete in a race. They both start at point A and finish at point B at the same time, but did they run at the same speed? Runner 1 took the direct route, covering a distance of 100 meters in 10 seconds. Runner 2 took a winding path, covering 150 meters in the same 10 seconds. Average speed is the total path length divided by time. Runner 2 has an average speed of 150 meters divided by 10 seconds, which is 15 meters per second. Average velocity, on the other hand, is displacement divided by time. Both runners moved 100 meters east, the displacement from A to B, so their average velocity is 100 meters divided by 10 seconds, which is 10 meters per second east. So runner 2 has an average speed of 15 meters per second, but an average velocity of only 10 meters per second. Speed measures how fast they're moving along their path, velocity measures how quickly they're changing position. When are they equal? Only when the path is straight. Runner 1 ran straight from A to B, covering 100 meters of actual path and 100 meters of displacement. Speed equals velocity, both are 10 meters per second. Your car's speedometer shows a specific speed at this very moment. But mathematically, how do we define velocity right now if velocity requires a change in position over time? The trick is to use smaller and smaller time intervals. We start with a large interval, say from t equals 1 second to t equals 3 seconds, and calculate the average velocity. Now let's shrink the interval from t equals 1 second to t equals 2 seconds. Even smaller, from t equals 1 second to t equals 1.5 seconds. As we make the time interval infinitesimally small, the secant line becomes the tangent line to the curve at that point. The instantaneous velocity is the slope of the tangent. The tangent line at t equals 1 second makes an angle with the time axis. The slope of that tangent line is the instantaneous velocity at exactly t equals 1 second. Now look at the tangent line at a different point, say t equals 3 seconds. The curve is steeper there, so the tangent has a larger slope. The instantaneous velocity at t equals 3 seconds is higher, maybe 5 meters per second, because the car is accelerating. When you press the accelerator, you're changing your velocity over time. But how do we measure how quickly velocity changes? Acceleration is the rate of change of velocity with respect to time. Just like we use the derivative for velocity, we take the derivative of velocity to get acceleration. On a velocity time graph, acceleration is the slope. Just like velocity was the slope on a position time graph, if the line is steep, acceleration is large. If the line is flat, acceleration is zero. Now, here is an important distinction. When velocity and acceleration have the same sign, the object is speeding up. When they have opposite signs, the object is slowing down. Let's say a car is moving forward at 20 meters per second. If the driver presses the gas, acceleration is positive and the car speeds up to 25 meters per second. Velocity increases, acceleration is positive, same sign. But if the driver presses the brake, the acceleration becomes negative while the car is still moving forward. The car slows down from 20 meters per second to 15 meters per second. A velocity time graph can show all this visually. A steep upward slope means strong positive acceleration. A gentle slope means weak acceleration. A flat line means zero acceleration. A downward slope means negative acceleration. All the kinematic equations for motion under constant acceleration come from one fundamental relationship. Acceleration is the derivative of velocity. From this definition, we can rearrange and integrate to find velocity as a function of time. If acceleration is constant, we get v equals u plus a times t. Next, we use the fact that velocity is the derivative of displacement. So displacement s equals the integral of velocity with respect to time. Integrating, we get s equals ut plus 1/2 at squared. This is our second kinematic equation. To get the third equation, we eliminate time. We start with v equals u plus at and solve for t. Now substitute this expression for t into the second equation. S equals ut plus 1/2 a t squared. After simplification, we get v squared equals u squared plus 2as. This third equation is useful when time is not involved. These three equations are valid only under one condition, constant acceleration. If acceleration changes, these equations don't work and you must use calculus directly. Let's see how to choose which equation to use. If the problem gives you initial velocity, acceleration and time and asks for displacement, use equation 2. Drop a ball from a window, it falls straight down, accelerating due to gravity. On Earth, the acceleration due to gravity is a constant 9.8 meters per second squared, often written as lowercase g. In free-fall problems, we neglect air resistance and assume gravity is the only force acting. The value of g is approximately 9.8 meters per second squared, or sometimes rounded to 10 meters per second squared for estimation. Now here's the key. We need a sign convention. Let's say downward is negative direction. So the acceleration due to gravity is a equals negative 9.8 meters per second squared. If an object is thrown downward, its initial velocity is negative. If thrown upward, initial velocity is positive. If simply dropped, initial velocity is zero. Let's apply the kinematic equations to a concrete problem. A ball is dropped from a height of 45 meters. How long does it take to hit the ground? Substituting into the equation, we get negative 45 equals 0 times t plus 1/2 times negative 9.8 times t squared. Simplifying, negative 45 equals negative 4.9 t squared. Taking the square root, t is approximately 3.03 seconds. So the ball takes about 3 seconds to fall 45 meters. What's the velocity when it hits the ground? Use the third kinematic equation. V squared equals u squared plus 2as. Imagine two trains on parallel tracks moving toward each other. From the ground, train A moves at 30 meters per second east and train B moves at 20 meters per second west. From the perspective of a passenger on train A, how fast is train B approaching? The velocity of object B with respect to observer A is calculated as the velocity of B minus the velocity of A. We write this as VBA equals VB minus VA. In our example, VBA equals negative 20 meters per second minus positive 30 meters per second, which equals negative 50 meters per second. Let's try a different scenario. A boat is moving east at 10 meters per second on a river. The river current is flowing east at 2 meters per second. What is the boat's velocity with respect to the ground? The boat's velocity with respect to the ground is V-boat ground equals V-boat minus V-water. Wait, actually let me recalculate. We want V-boat with respect to ground. So we add the boat's velocity relative to water and the water's velocity relative to ground. But now the boat wants to cross the river, which is 100 meters wide, flowing at 2 meters per second. If the boat aims straight across at 10 meters per second relative to the water, it will drift downstream due to the current. To find how far downstream the boat drifts, we use the fact that the drift velocity is 2 meters per second. As the boat crosses 100 meters at 10 meters per second, the time taken is 100 divided by 10, which is 10 seconds. During these 10 seconds, the river current carries the boat 2 meters per second times 10 seconds, which is 20 meters downstream. Now let's consider a police car chasing a speeding car on a straight highway. The speeding car is moving at 40 meters per second and the police car is moving at 35 meters per second, both eastward. What is the relative velocity? The velocity of the speeding car with respect to the police car is V speeding minus V police, which is 40 minus 35 or 5 meters per second. Imagine a long road trip. For the first hour, you maintain a constant speed of 60 kilometers per hour. For the second hour, you accelerate from 60 to 80 kilometers per hour. How do these two segments look on a position time graph? During the first hour of constant velocity, your position changes by a fixed amount each minute. 60 kilometers per hour means you travel 1 kilometer per minute. The graph is a straight line with constant slope. During the second hour, you accelerate, your velocity increases, so you cover more distance per minute as time goes on. The position time graph curves upward, getting steeper and steeper. Here's the key. For uniform motion, the graph is a straight line. For uniformly accelerated motion, the graph is a parabola or at least a curved line. How do we tell if the object is speeding up or slowing down? Just by looking at the graph. If the curve is getting steeper, the object is speeding up. If it's getting flatter, the object is slowing down. Mathematically, the slope of the position time graph at any instant is the velocity at that instant. The curvature tells us about acceleration. If the curve is concave up, acceleration is positive. If concave down, acceleration is negative. Let's look at a worked example. A car travels from rest with constant acceleration, 2 meters per second squared for 5 seconds. Draw the position time graph. Connecting these points traces out a parabola. At t equals 0, the curve is flat, velocity equals 0. As time increases, the curve gets steeper, showing increasing velocity. You're driving at 20 meters per second when you see a red traffic light ahead. Your brain takes time to react, then you brake. The total stopping distance has two parts, the reaction distance and the braking distance. During the reaction time of 0.75 seconds, the car continues at constant velocity. At 20 meters per second, the reaction distance is 0.75 seconds times 20 meters per second, which is 15 meters. After the reaction time, the driver applies the brakes. The car decelerates from 20 meters per second to 0. Let's say the deceleration is 8 meters per second squared. To find the braking distance, we use the kinematic equation v squared equals u squared plus 2as. Since v equals 0, we get 0 equals 20 squared plus 2 times negative 8 times s. The total stopping distance is the reaction distance plus the braking distance, 15 meters plus 25 meters, which is 40 meters. Now here's the crucial part. What if you were driving at double the speed, 40 meters per second? The reaction distance is now 0.75 seconds times 40 meters per second, which is 30 meters. Already the reaction distance has doubled. But the braking distance increases dramatically. Using v squared equals u squared plus 2as, we get 0 equals 40 squared plus 2 times negative 8 times s. The total stopping distance at 40 meters per second is 30 plus 100, which is 130 meters. Compared to 40 meters at 20 meters per second, doubling speed more than tripled the stopping distance. In fact, let's show the mathematical relationship. Braking distance is proportional to velocity squared, s equals u squared divided by 2a. If you double velocity, the braking distance increases by a factor of 4, and that is a wrap on motion in a straight line. We started with something as simple as where are you, position on an axis, displacement as a sign change, path length as total ground covered. Then we gave motion a rate, average velocity, instantaneous velocity, the slope of the xt graph at a single frozen moment. Acceleration told us how fast velocity itself was changing. And when velocity and acceleration point in opposite directions, that's how things slow down. From calculus, we derived the three kinematic equations, step by step, no magic, just integration. Free fall showed us nature's own acceleration, 9.8 meters per second squared, pulling everything equally, air resistance aside. Relative motion reminded us that velocity is always measured from somewhere. Change your frame, change your numbers, and stopping distance showed us why physics is life-saving. Double your speed and your braking distance multiplies by 4. If this helped you see motion a little more clearly, hit like, drop a comment with your toughest doubt, and subscribe so you never miss a chapter.